So, hi, I'm Adam, and I was working on how to verify for Cardano, at least tooling that will make your life easier if you want to create one, for the last, I'd say, 2 years. And this talk will be a bit different. It will not be theoretical. It will be from the developer perspective, which means how you would use that tooling, and I will also provide you with some core concept, such that if you will see examples, you will know why they look like that. In this presentation, you will see first general intro, like review of what's there to use, which there are a few papers, there are a few libraries that are based on those papers. Then I will present very, I would say, a medium level advancement use case for Cardano, which will be ATMS, which is verifying a bunch of signatures from members of a committee. If you know Mithril, you probably are familiar with that concept. And then we do code walkthrough with Rust and Plinth, how the internals looks like, and then I will try to run it. If it will not blow up, then it will run on preprod. So first, why may you be interested in using zero-knowledge proofs at all? So first, it allows you to split computation, or to say it differently, you can offload some expensive computation to off-chain code, and then you can verify that those computations were carried in a specific way on-chain, but not by repeating them, but just verifying a proof. And if you use correct tooling, then the verification on-chain is pretty cheap and does not require a lot of data. Especially, it may not require for you to put the same data that you use for computation on chain. Instead of that, you can, for example, commit to the data, which is fancy name for hashing it, and then you check it in circuit and you put only hash of the data on chain, which gives you a lot more headroom in terms of transaction size, which for Cardano is 16 kilobytes, as you know. And another nice feature is that the data may be small, but they may be private. Or because of GDPR, because of you name it, you cannot publish it on public blockchain, but you need to perform computation using the data. And this zk-SNARKs, or zero-knowledge proofs in general, are a very nice tool if you need to do that. So then, how you do it? So first, you define your computation. Then you split the data into private and public. And then you perform a step that is called arithmetization, which means that you take your program and you translate it into first execution trace and then polynomials, which is a hard step. And in practice, you don't just translate random program, but rather you are trying to build your program using components that are already translated. And there are many pieces that you can put together and then approximate what you actually wanted to do with your proof. Then you use cryptography machinery, which is interactive oracle proof, and polynomial commitment schemes that can take your arithmetization and produce and compress it and produce a proof that you can then hand over to somebody that you want to convince that you actually did what the computation is supposed to do. And then you have another piece of software, which is called verifier, that accepts that proof generated in the previous stage, accepts the public data, and says yes or no, which is the proof valid, is it invalid? So this is very high level, as you can imagine. So let's apply this to some abstract example. Let's say you have an authority like a government or Visa or MasterCard that are issuing you a card, and let's say you have a hotel that requires you for the booking to have at least $500 on the card. So you would like to prove to the hotel owner that you have the money, but you don't want to reveal your account balance, let's say. So then what you can get is that authority issues you a certificate. The certificate is signed by the authority. So the naive thing to do is just hand over the certificate to the hotel owner, but then you reveal all the data. But you want to only selectively reveal the data. So you construct a circuit which inside compares the certificate, verifies if it's signed by correct authority and that it actually contains specific values in a specific field. And you can hand over that proof to the hotel owner, which can run it with publicly known public key from, let's say, card issuing company. And then you will have the case where you prove something to this hotel owner, to the third party, but you don't want to reveal everything. Okay. So that would be for the example. And then tools that are around right now is that you have mostly they are based on white papers, and they are the names are also from the white papers. So the original one was GROT16, which described the arithmetization, but it has this feature, let's say, that for each use case that you want to, for each circuit that you want to run with GROT16, you need to perform a step that is called trusted setup. And then you have to convince the other party that you did the trusted setup in a correct way, such that you cannot forge fake proofs. So the next in line, I would say, was Plonk paper. And then the improvement, among many other improvements, was that you can have trusted setup, but not for a specific circuit, but in general for all the circuits that you would like to run with Plonk. And then, based on Plonk, the extension of Plonk, let's say, was implemented in Halo 2, which is not a paper, it's a library with some documentation, which adds a very nice abstraction when you want to use basic components, and from those basic components build larger, more complex circuits. And there is further evolution in terms of trusted setup. It's called zk-SNARKs. There are libraries like Plonky2, Plonky3, which requires no setup, but the payoff, the balance is that the proof produced by zk-SNARKs are not small. They are like proofs from Halo 2 that you will see can be around 2 kilobytes, where from SNARKs they are more around tens of kilobytes, even hundreds of kilobytes, so they will not fit into a single Cardano transaction. And other part why, for example, why we picked Halo 2 is that Plinth have specific built-in functions to work with primitives that are also used for Halo 2, specifically BLS 12 curve operations and pairing checks. Okay, so let's dive deeper into Cardano. So if you want to do zk proof verification on Cardano, this will be like a step-by-step guide. First, you create your circuit. This is standard for everything. Then you generate the proof using a Halo 2 functionality. Then you export that proof such that you will be able to import on the Cardano side, and it will mean the same in terms of Plinth built-in primitives. Then you implement Plinth verifier, which is part of code that will work with the imported proof. And then you construct transaction, and it's done. Easy, right? No, because this is the hard part, because this, as you can imagine, is custom part that you would have to implement for every circuit that you do. And there is some specific mathematical equations that are specific to some components that you use, and you would have to, for each such circuit, like start from scratch. So one idea that maybe is like, instead of implementing this from scratch, you implement a generator, which will derive rules from the circuit and just generate this part for you. And recently, there was a library open sourced from IOG, which does exactly that. So it can read your circuit description in Halo 2. It can then extract all the specific equation, put it into Bluetooth code, and then also is able to export the proof, or even generate the proof using primitives that are very friendly to to Bluetooth built-in function, such that if you call them on chain, it will not explode. Actually, it fits into a single transaction, which is a very nice property. Okay, so now for the code example. it will be ATMS, which is algorithm that you have that you have a committee, let's say 400 signers, and you have a message, and you want this message to be signed by, let's say, at least 200 people from the committee. And if that happens, you gather all the signatures, all the public keys, all the messages, and of course the specific circuit. You shove it into Halo 2, and you get a proof. And on the other side, that I would like to run on Cardano, I get the proof, I get the relevant public inputs and specific verifier contract, send it to Cardano, and if and only if the proof is valid, I would like to mint something on chain. So let's say NFT. Okay, so one precondition, this is still in proof of concept stage, so it's good for experimenting, but there were no security audits so far. So if you want to use it, you are responsible for doing your own security audit or whatever. Okay. So first thing that I would like to show is how the circuit is set up for the code generation. So this is the circuit. It's also open source, but in a different repo. As you can see, you provide a signature, public keys, a hash of those public keys, then message, and threshold that you require. Pretty standard. Because this is standard Rust structure, the magic happens below because there is a trait called circuit implemented for this structure, and this trait is responsible for constructing, wiring, and setting up all the internal circuit machinery for this, such that the fields you provide actually will do what they're supposed to do.
Are we expected to write this circuit's
No.
implementation?
No.
So we just take it from
This is, I just take it from the open source library for zk-SNARK that was also open sourced by IUG. So no, this is like a real developer experience that you would just pick it off the shelf. Of course, you have to check if it has all the security audits and whatsoever, but this is how you would use it. So you have a structure, you initialize the structure, and then you do this trusted, you're supposed to do trusted setup here, which is a fancy name for KSDG params. But here I'm doing untrusted setup, which I'm just using randomness to generate some parameters that are required. This is not what you're supposed to do on production, but for testing it's very convenient.
Can we use the towers of Tau from Ethereum, for example?
Of course, you can use trusted setups that were run by other, but I would have to serialize it, load it, and whatsoever. Here it's just one call to give me random setup. But yeah, you can use those you mentioned. And then this is like the entry point for the code generation in Plinth. This is stuff implemented by me, and it actually gets all those parameters from above, and it uses templates, which are specified somewhere around here. Oh, here. And those templates are for specific flavors of KZG, because we support two, but for this example, I will use the older one, let's say. And what you do is you use cargo, because this is Rust, and so you just run an example from Rust, which is a program that will process the circuit and then generate a data structure describing the circuit and then transpile every relevant piece of information into a Haskell file. And this actually two Haskell files, because one Haskell file contains all the constant relevant to the computation, and this is actual logic relevant to the computation, which you can see is just a function in Haskell. So you can import it, use it however you like, but you have to provide the proof and all the public inputs that were specified in the circuit. Right? And then what's also important is that despite it may look like a blob of text, it's structured blob of text. And if there is something off, you want to add new feature, those equations and operations are mapped one by one with the original Halo 2 verifier, which is like source of truth, how it's supposed to work. And then all those equations are combined into a pairing check. And here you can see call for the built-in functions that are doing pairing check from Plutus. Okay.
That's the on-chain verifier, right?
Yes, this is Haskell. This is on-chain verifier.
So all those mathematical or multiplication, all this stuff is gonna happen
On-chain. On-chain. Yes.
Is it enough budget for this?
Of course.
All right.
Yeah, it is. Maybe, of course, was too strong of a sentence, but there is. Okay. So far we have set up for the code generation. We did generate the code. So now we have to generate the inputs for this. Maybe not yet. So first, let's connect the verifier to something that it will actually look like a minting policy. So first, this is standard import. I'm importing the function, and then there is a thin wrapper which expects a message to be signed, public key commitment, and the proof from the redeemer. Pretty standard stuff, right? You provide them as an input to the transaction. I'm hard coding the threshold, so I'm always require at least 3 people to sign, and then I'm just calling the verifier. The verifier returns a Boolean and some tracing data. If you omit them, nothing happens. But if you want to test and, for example, easily see what are those intermediate values that you see here, you can just add them as a list, and those will be printed out by the tests that are also part of this repository. But for execution and on-chain, those are ignored.
Sorry?
Yep.
And is budget constant? You don't have any loop or anything?
Is budget constant? Mostly yes, but it can depend how your UTXO that you used into a transaction look like. But in terms of execution, it's mostly constant. Yeah?
Is the threshold one used for the multisig or is it for verification?
No, for multisig.
Okay.
How many members of committee you want to sign the message?
What kind of programs can you basically represent as zk proof?
So the correct answer is every program that you can arithmetize.
And what programs are those?
But it's not
Uh,
the only Turing complete from that.
I'm not sure. I'm off the top of my head. I cannot answer your question, but there are many. I mean, in terms of Halo 2, it's usually stuff related to signatures, but you can also verify state transitions and stuff like that. But maybe the more correct answer would be the programs that you can express using the circuit that are available and tested, because for the developer perspective, this is what you would go with. You would not design a new circuit, new chips, but rather pick something off the shelf and try to wire them together.
So you could, in theory, have a programming language which compiles to...
Yeah, okay, I forgot about that. There is actually RISC-0, which is zero knowledge version for RISC-V, and if it's something compiles to RISC-V, you can probably create zk proof for that. But I didn't work directly with that, so this is a very theoretical answer. Okay, more questions? Okay. So, okay, this is like a thin wrapper just to plug in the verifier such that it can be used for minting as a mint verifier. So then I just do cabal run, and gen mint is actually this piece, which takes scripts, compiles it, and then does all those steps to get nice UPLC hex file, which I can later use from the Rust side. And then here's the Rust side. So I have to repeat the same constant because the proof has to match, the proving part has to match the verifier part. So I have to generate 3 signatures. So this is why it's hard coded. Here I provide the message that I would like to sign. Of course, it's 42. And then I'm using this helper function, which is nothing fancy, just accepts number of parties, threshold, message, and generates a lot of keepers. Then from those keepers, randomly selects threshold number of parties to sign, then generates those signatures and returns everything from this function. Also, it calculates the public key commitment, which is, again, fancy name for hashing all the public keys by concatenating them together and then throwing them into this hash function. Okay, and when I have all of those, I can, again, construct the same circuit, but this time with real data that I would like to create proof about. So you can see I'm just passing in signatures, public keys, public commitments, message, and threshold. And I'm also constructing public inputs. And you can see that I'm reusing some of this data for public inputs. And this is useful because then the prover, then the verifier that gets the proof can infer from those public inputs how the actual private input look like. But as you can see, I'm not passing everything. I'm hiding, for example, how the signature look like and hiding how the actual public keys, what public keys were used. So in theory, I could, for example, replace this very naive hashing with Merkle-Patricia tree root and provide you only with a root of a tree and then path for a specific key to convince you that actually this key among other keys signed the message or do fancy stuff like that, but it's outside of ZK. Okay, and then I'm using a function. This is provided by Hello2. This gets my circuit, of course, zk param, which I did with not trusted setup, and then creating a proof, and then finalizing the proof. Finalization just dumps everything into blob of bytes, which is nice because then I can use this blob of bytes when creating transaction for Cardano. And here you can see creating transaction for Cardano. And interesting part would be this one, which I'm getting this public key commitment, a message that I want to sign, and this blob of bytes. I'm packaging that into a redeemer, and that's all. There is nothing else. Everything else happens on the Bluetooth side.
I like your execution calculation for the key. I like how you
Yeah, it's max. It's testing. I don't want to deal with that. It's just max. Okay, I'm building this transaction with Cardano serialization lib, which is native to Rust, but you can use whatever, JavaScript, Bluetooth, Cardano, CLI, whatever you want. And then I'm submitting a transaction using Blockfrost, and that's all, because after assembling, I'm just submit, and that's all. So now, if it will all work, it should not this one, it should actually. And submit transaction is just a binary program in Rust. So this time I generated new committee from entropy. The public key commitment looks like this. The message that I signed looks like this, which is of course 42 in hex notation. And it actually created a transaction, submitted this on chain. And if no. Sometimes it takes a while from. Yeah, sometimes it takes some time from Blockfrost to be propagated to C Explorer. Here it is. Okay, so you see, it takes some space, but you still have 1 kilobyte for extra data. And then, yeah?
Is this script a reference script or embedded? So probably embedded, right?
Yes. Yes, you can optimize that. Yeah. Yeah, but you can also treat that contract as an oracle, and that oracle can produce NFTs, and the name of NFT can encode actually. You can hash a message and everything else into a name of an NFT, and because of that, because the origin of an NFT would be this contract, then you can program around that this NFT will replace the computation. You can chain it down the line. Okay, and this is the contract, and this is the input. 42 is clearly seen, but this one is in this strange format. But you can see that it's 2481 something, and in decimal it's 2481 something. So those are actually the public inputs. So it actually works on chain. So now you can probably think, what happens if I do something like this? Because that would be more interesting example, right? And I can actually start this right now. And we will probably sit here around, wait for another 40 minutes, because I did run it yesterday, and it takes 40 minutes. So I will kill it. And actually, I have a transaction hash from yesterday. Of course, 40 minutes on M1 Max. So if you use like standard servers, it will be faster. And you can also run Halo 2 prover using GPU acceleration. So it also makes it faster. And this is transaction from yesterday. So there was a question if the time is resources are constant. They are more or less constant because you can see similar script size, similar everything else. But I'm not sure how to check here the CPU usage and memory usage. But from what I know, they are very, very close. And if you go to the maybe I will spoil it a bit, but if you go to this open source repository from IOG, then you can see that we did some benchmarks at the bottom. And if you compare ATMS to ATMS, it doesn't change. Right? The computation, the CPU usage and memory usage is the same. Even if you get 50 out of 900, sorry, 50 out of 90 signatures is equivalent to doing 228 out of 408, which is also a very nice feature for the ZK because those are the thing that changes and that may hit you is actually off-chain. And the off-chain part you can optimize with the technique I mentioned. So if you have, and of course you probably know that ATMS may be also applied to other parts like Mithril certificates, but you have to extend it. Okay, so that was questions? Yeah?
I'll go with a simple question. I just want to make sure I understand correctly. This is transpiling the circuit into the verifier, so every circuit has a different
Yes.
verifier on chip.
Yes.
And so from an auditing perspective, you would need to audit.
Yes, yes, you would need to audit. Yes, and this is why I mentioned this proof of concept because there was no auditing. But with formal method, maybe you can also certify the transpiling process itself.
When will that be done?
I probably should ask James. Yeah.
I think he was first.
Okay.
I asked many questions. Just go on.
Okay, no. Just out of curiosity, I would like to take a look at the template. Can you show it?
Template?
Used to compile the verifier.
Uh,
The verifier.
Okay, okay. I will because there are different ones. So this is handlebar template. There are because besides those templates, there are also those bunch of primitives that are used with this templating, such that it is still human readable stuff. But the templating is like there are specific parts of Halo 2 verifier that are run each time, and each of the section of the verifier has its own dedicated place where the stuff are plugged in. So for example, here you have proof extraction steps. So this is the whole processing of the proof. And then you have gates related equations. Also, my circuit didn't have lookups, but Halo 2 circuit can have lookups, and they have also specific equation that you have to extract. Then you have permutations, which are how the circuit is internally wired. And then, okay, more related to lookups. And then you have things that is called internally, because I'm trying to stick with Halo 2 terminology, those are queries that you construct, and from those queries you then construct one big computation, which is called multi-scalar multiplication. Okay. Yeah?
How difficult it is to create these circuits for this to work? Like you have this ATMS.
Yeah.
If I want to do, I don't know, Bitcoin block validation.
So it's significantly harder for Bitcoin block validation because there's much more structure. And it's case by case. It's like a specific project to create a circuit for a use case.
Like, I don't know how Halo thing works, but I know there are like higher level languages or DSLs that create the circuits that can be used then in different, like in growth 16, for example. Other things like that for Halo?
So yeah, Halo to itself is that DSL. So for example, if you go to this ATMS circuit and you see how, and not this one, this one? Yeah, actually this one. So you have the synthesize method, and in synthesize you have calls to other chips, and you create gates and chips inside the synthesize method, and you're connecting them.
Like, I need to have this circuit created somewhere, and then I program the connections, right?
It's like more you have, so for example, here you probably can find ATM SNARK gate, which is also gate is like internal terminology for Halo 2, let's say. And then this SNARK gate handles SNARK signatures because I'm using SNARK signatures for this ATMS. And you have ECC gate, and you have those gates that you have to wire together, if that makes sense. And there are libraries that are also open source that can provide you with different types of chips and gates.
So essentially those like built-ins, sort of. You just
Yes.
connect them as
Yes, but those built-ins, they have their own source code. So there should be something. Oh, no, combined. I'm trying to find them.
There are no compiler that just converts whatever a higher level language that manipulates these gates' functions that just compiles to that.
I think that was the design choice. You don't create new language, you just use Rust and its type system to build structures, because in the end, those languages have to be compiled down to structures that are, in this case, represented by the abstraction. Okay, I'm not sure I will find it right now to show you how the specific gates are, because there should be equation for. Oh, synthesize, okay. So for example, this no, okay, sorry, to not confuse you more.
I'm just thinking, it looks, unless its code is generated, if it's manually written, it's like large error and error prone, I think. So if you just connect different things incorrectly, right?
Yes, you can correct, you can do exactly the mistake that you're saying. Yes, but I think because then the other hand is you would have to specify the same relation between, because in the end those are abstraction, but in the end you specify a relation between data from your execution trace. And you see you see a large amount of code, let's say like that, because there are many relations that you have to specify. So
I think it should be generated, right? Rather than written.
yes, but then how would you define the generation logic?
Question.
Good question. Okay, let's leave it like a good question. So maybe one answer to the question was that you don't do this generation, but rather you do specific case and you audit specific case, because those circuits can be audited. And also I was asking James about this under constraint, over constraint formal verification that you can also run on your circuit.
Maybe you can generate it from EGDA specification.
I don't know, maybe.
Would be cool.
Different things may happen, but I'm not aware of the work that is pursuing this idea. Okay?
Could you just go back to the page where you have the benchmark results?
Yeah, of course. I can also probably do like this. Right.
what does the lookup table do?
In this case, it does nothing. It is artificial lookup table just to test how adding lookup equation impacts the ATMS.
Well, what would it do
In general, lookup tables are used for optimizing computations that are not easily encoded into specific field used for the proving. So, for example, I'm using a hash that I'm using here. So, for example, hash that you usually use for circuits is Poseidon, which is because it's optimized to be arithmetized. But if you want to use SHA-256, it's hard to implement directly in the field arithmetics, and because of that, you use lookup tables that you look up some stuff.
To understand correctly, that this lookup table can be of any size, basically.
It depends.
So that would be cool because you can like represent a function as a lookup table, right?
It doesn't exactly. It's not the topic of. So we can talk about it offline, let's say like that, because there is more caveats to that. It's not just a table. It's those are also equations.
No magic.
Yeah. Okay. So any more questions? Okay. So. Again, to reiterate, why would you use it? It gives you flexibility, as you saw. The part that is in the verifier, especially if you're using Halo 2, is pretty much constant per circuit, let's say, because if you change the size of the circuit, change the structure, the actual verification cost may change. But if you nail down the circuit to the specific size, it stays constant, and the proving size changes. And then you can switch public parameters. So, for example, I can use the same mint verifier to verify signatures from different committees, because I'm providing the committee members as a hash, and that hash doesn't require, changing the hash doesn't require me to change the contract itself, which is also a nice property. Okay, increase, okay. And then there's this thing that I'm not providing the public keys themselves. I'm providing only hash, so it also hides the identity, or hides everything about the public keys if I want. And then this is the repository that was open sourced. And this repository in the dependencies have the other repositories that were also open source that contain specific circuits. And it also contains this ATMS circuit if you want to dig deeper inside how it looks like. Okay.